We are going to investigate the behavior of radio wave, but first I'll show how the transmitter and receiver are constructed. Unlike my previous experiments using laser and microwave, I can't find ready-to-use devices suitable to investigate propagation of radio wave, especially on receiver side. So we need to make some modifications to commercially available radio communication module commonly used with microcontrollers. The package includes a wireless RF transmitter module, a wireless RF receiver module, and two nickel-plated spring antennae. Here is the detailed specifications. Here is how the transmitter looks like. The data pin is connected to positive power terminal through 1 kilo ohm resistor. We want a continuous radio signal transmission comes out of the antenna. The transmitter is supplied by a power bank commonly used for cell phones. Here is the receiver. The voltage of data output pin is measured by a DC voltmeter relative to ground pin. Let's see the RF modules in action. When the receiver is powered on, we get a spike in the voltmeter, but it backs down quickly. The same thing happens when the transmitter is powered on. This is not what we want to see. Let's move the transmitter so its antenna is in line with the receiver. The same thing happens. What we want to read from the receiver is the raw radio signal strength. Let's see if we can get it from the block diagram of integrated circuit in the receiver. It's shown that signal in the data pin has gone through a comparator, data filter, demodulator, and a bandpass filter. To measure the raw radio signal strength, we need to move the voltmeter probe from data point to output of buffer amplifier. Here is the receiver after modification. The cable from data output pin has been cut off. A new cable for measurement has been connected to output of buffer amplifier. For convenience, the bandpass filter pin connected to the amplifier is selected as soldering point. It turns out that the buffer amplifier is a bipolar circuit block, while the power supply is unipolar. So we need to create a virtual ground as signal reference, which can be easily produced using a potentiometer as voltage divider. When the virtual ground is set to minimum or connected to ground, the signal voltage is around 1.76 volts. Without the transmitter, the reading should be close to zero, but the potentiometer setting is hard and easily overshoot. To make the voltage adjustment smoother, some resistors can be added to the potentiometer as shown here to reduce the slope of VR curve around the desired value. Now the modification is finished. We can make the voltage close to zero when the transmitter is off. Although we can see some small drift, it's not so significant compared to the signal from the transmitter.